Alright, in this video we're going to look at what are called series. And so a lot of the videos I've been making in this section up to this point have been leading to this discussion. And so the way I've organized things in the past I think will make sense after this video, hopefully. I'm hoping you can, for my students at least, you can see the logic of what we've been doing the last few videos. So it says consider the sum 4 plus 9 plus 14 plus 19, etc. And it says find the sum of the first 3 terms and the first 100 terms. And so when you see that word sum, I want you to think of series. So a sequence is sort of like the list of numbers. We know that the sequence in this problem would be just the numbers 4, 9, 14, and 19, which I've arranged here in a table just to remind you that a sequence is a function. But the series would be, well, if I wanted to start adding those terms up. And so what I'm going to have you do is make another column here. And I want you to call this column S of n. S stands for sum, and sometimes it's useful to think of that sigma term, or the sigma symbol being above that column to remind you that now we're adding up the terms. So the first thing we got to do is pretty easy. Find the sum of the first 3 terms. So I'm actually going to do more than that. I'm going to find the sum of the first term. Well, the sum of the first term would just be 4. That was easy. The sum of the first 2 terms would be 4 plus 9, which is 13. So I'm going to write 13, but I'm going to remind you that that's just 4 plus 9. And then the sum of the first 3 terms would be 4 plus 9 plus 14, which is 27. So that's 4 plus 9 plus 13. Alright, and so far, so good. Now we have to come up with the sum of the first 100 terms. So I'm going to put 100 here. And so ultimately what we want is the sum of the first 100 terms. Now I'm going to put a box here because we don't actually know what the 100th term is yet, right? And then therefore we don't know what the sum of the first 100 terms is either. So let's do something more powerful than that. Let's actually come up with a formula for the sum of the first n terms. So I'm going to put an n here. And let's see if we can fill in these 2 bottom boxes first. Now the second column, the function column, we can actually come up with a formula pretty easily because this is an arithmetic sequence where we're adding 5 every single time to get to another number. And so that would mean that the formula is 5n. And I'm supposed to get 4 out when I plug in a 1. Right now I'm getting out a 5, so I got a minus 1 to fix that. Alright, so now let's use the method we've explored earlier, which is Gauss's method, to come up with a formula for the sum of the first n terms. So in other words, I'm going to get a function, sort of like a sum function, and once I come up with that, I'm just going to plug 100 into that. Okay, so we're doing something more powerful than what the question asks, but it's going to be worth it afterwards. So let's remind ourselves of what Gauss's method said. It would say that the sum of the first n terms would be, well, in this case, 4 plus 9 plus 14 all the way up to the 5n minus 1. So the term just before that, just to give us something else to look at, would be 5n minus 6, 5n minus 1. That would be the expression for the last 2 terms. Now if we write them backwards, we get 5n minus 1 plus 5n minus 6, etc. And then the first 2 terms would be a 9 and a 4. So we add these, and our answer is 2s equals, so the 4 plus the 5n minus 1 gives me 5n plus 3. The 9 plus the 5n minus 6 similarly gives me the 5n plus 3. So we know how this works, right? We've seen this. all the terms are 5n plus 3. Oops. All right, and so what's the next question we ask? Well, we ask how many there are, and I claim this is really easy. There's n of them. And I'm going to put a little note, see your table. Because if you look at the table, clearly we're adding up n terms, because 5n minus 1 is next to the n in our input list. All right, so we know there are n of them, so that means that 2s equals n times 5n plus 3. And so now we divide by 2, and we get our answer. So I'm going to write my final answer here, I'm going to write s of n. I'm going to kind of introduce this function notation here. S of n is equal to n times 5n plus 3 divided by 2. And so there it is. I found a formula or a closed form for the function, the summation function, that tells me the sum of the first n terms. And so all I need to do now is plug in 100. So when I plug in 100, oh, by the way, we should plug in 100 into our general rule to see what the 100th term is. I'm going to plug it into here. 5 times 100 minus 1 is 499. So in other words, we'll be adding up all these numbers until we get to the term that says 499. So S of 100 is equal to 100 times 5 times 100 plus 3 divided by 2. And let's see, that's equal to 100 divided by 2 times 503. And that, if you put it in the calculator, gives you 25,150. $25,150. All right, so we answered the question, but again, we kind of took a tour of something more important, which is that we came up with a formula. So what I want you to see is that we have a nice organizational tool here, a table, which tells us that our sequence can be expressed as a function. That's our first or our second column. And also that the sum of the first whatever terms you're interested in can also be expressed as a function. And we figured out the formula just by using Gauss's method, which we had seen earlier. All right. So the next page, we're just going to formalize some of this, and then also ask another interesting question, which would be, what happens if we just decide to keep adding up these numbers and never stop? All right. So here I'm defining an arithmetic sequence, which was one we just looked at. And an arithmetic sequence would be, in this case, I'm calling it capital A of n. So it's another function of the number of terms that you have. And it's equal to, so I'm going to use sigma notation, the sum of all the terms in your sequence, so that's lowercase a, as k goes from 1 to n. So we just found, just a little note, I'm using a instead of s, but we just found a of 100. Although technically we got s of 100. I just used the letter s instead of a. So s of 100 in our case. Now, to just finish this up briefly, the question we have here is calculate the infinite sum if possible. So the infinite sum basically means we're never stopping. All right, so let's start with just this idea that, well, in sigma notation, what would my rule look like? Well, it would be k goes from 1 to infinity, and the rule we had in the last page was 5n minus 1, but I'm going to put a k minus 1 here. So if you plug in k equals to 1, you get a 4 plus a 9 plus 14, etc. Now I'm going to put a dot, dot, dot. The question is, when we add up all these forever, what value does that approach? Now again, you can't really add anything up forever, but the idea is what number would that approach? And so hopefully your intuitive understanding of adding should suggest that this is going to be infinity, right? You're just going to keep adding numbers and you're never going to stop. And for reasons that you'll see later on in the next video, I'm going to use the actual formula we came up with to further confirm that that's indeed what happens. So there's our rule for adding up the first, so this would be like s of infinity here, for adding up the first n terms. So if we just keep adding up terms and never stopping, I'm putting an infinity in here, and it doesn't take a genius to determine that, well, clearly infinity times 5 times infinity plus 3, well, that's just infinity. Alright, so nothing interesting happens when we keep adding these numbers up. The result is just infinity. Alright, so we have a formal definition of an arithmetic series, and we just took a look at what's called an infinite series, which I'll talk about more in a future video.